Our next problem is going to be very similar to what we solved in the previous video. But now, instead of having the square term in our gradient, we only have the absolute value. And this is going to be a bit trickier than before. But anyway, let's do what we did before. So we are evaluating the directional derivative for any function v, right? And so all we do in the first step, it's very easy, we just plug in into wherever u is, u plus tv. So we have the integral of the gradient of u plus tv plus u plus tv minus u0 squared. Now, the second part is exactly the same as before, right? Recall, before, we also had the same exact term. And when we actually squared it and derived it and plugged in 0 into t, then we were left with u twice of, right, I canceled the 2 at the end, but we got twice of v times u minus u0 at the end, okay, inside the integral. So let's just simplify this and say this is just going to be equal to the integral of whatever the first part is, and then we're going to add twice of v times u minus u0. Okay? Now we just have to figure out what the first part is. So maybe it's a better idea to just write it like this and keep the derivative evaluated here. Maybe I should write the derivative like this at t equals 0. Okay? So hopefully this makes sense. Okay, so what's so tricky about the first part? Well, before we had a squared, now we have an absolute value, and this kind of messes things up a bit because we have to think about what that actually means, okay? Anyways, this is going to be, remember what the absolute value of a vector is? It's let's see, the absolute value of a vector v. This is v dot product v to the 1/2. So that's what we have to do. But v right now is, maybe I should have chosen a different letter, like y. Okay. Anyway, our y right now is nabla u plus t nabla v. So we have to dot product that with itself, and then we have to take the square root, and then we have to derive it. Okay? So first of all, letting y equal to nabla u plus tv, this is going to be del u dot del u plus 2t del u del v plus t squared del v del v. Okay? And then we have to take the square root of the whole thing, right? So all of this is here. And then we have to derive this with respect to, we have to derive all of this with respect to t. And then we have to add this part in, right? paste. Right, we have to add this part in. It's going to make it smaller. Okay, let's line that up. Not perfect, but it's okay. Okay, and so we have to use the chain rule here because we have a square root function. So what do we get? We have, let's see. So the derivative of a square root function is 1 over 2 root x, right? Okay, so we're going to have on the denominator the square root of this whole thing here. I'm just going to erase this. I'm going to copy the square root. Okay, let me erase one of the square roots that I wrote before. So this is the denominator. Of course, we're plugging in t equal to 0. So even though we just calculated the denominator, this part and this part goes to 0, so we can ignore all of this. Okay, but on top, what do we have? On top, we have to calculate the derivative of whatever's inside with respect to t, and then evaluate at 0. So remember what we said about ignoring terms? Therefore, when we're calculating the derivative of whatever's inside, we can ignore this part and this part. The first part because there's no t, the second part because t has a power. Okay, so all that's left is here. We're going to derive it with respect to t, and so we get 2 times nabla u nabla v. Okay, plus this part. Okay. Okay, now let's erase the 2's, and furthermore, the square root of a vector dotted with itself is really just the size of the vector, right? So you can rewrite the denominator one last time to be that. Okay, and we have this dotted with v plus 2v u minus u0 dx. Now, remember before we used Green's theorem to turn nabla v into a v? How do we do that? Well, okay, let's separate these for now. The first part of the integral is going to become something evaluated on the boundary, something, but it's all going to be 0. Why? Because we're in the space h1, 0. Anything evaluated on the boundary is 0. Minus the gradient. Okay, let's write the minus inside. U over that times v, and now because we have a 2v u minus u0, I can group these, right? Why did I change color? Right. All of this multiplied by v. And this has to be true for all v. What has to be true? All of this has to equal 0. For that to make sense, the inside, this part, has to equal 0, right? So that's it. That's the Euler Lagrange equation. to clean it up one last time, we're going to have this plus 2 times u minus u0 being equal to 0. And this is our solution.